started. We can take a break in the middle. That's fine. Okay. I'm delighted to be here and share with you what I know the best in terms of polymer characterization or polymer science in general. I'm going to hopefully use the next 3 hours or so, summarize, give you a very updated understanding of what's going on in the area of rheology. But I want to motivate it, give you a little broader perspective. So, you know, by now I probably, you should know, every year we consume several 100 billion pounds of polymers, several 100 billion pounds. We don't eat them, but we still nevertheless consume. Every year we produce that much. Most of it, you will find, I have items here, most of it, we use them because they are mechanically good enough. For packaging, for anything, there's a variety of items I have here. So it's mainly for their mechanical properties. In other words, their mechanical behavior is simply good enough. Of course, there are issues about, hey, if it's good enough, can I use a thinner piece of sample? Can I save and use less? And when you have a new polymer, is that new polymer going to be strong enough mechanically or not? So these are the questions you have. And the objective of polymer science, I think, a large part of it, should be about whether I can make my polymers stronger mechanically. So usually we look at this relation, you know, this magic thing. Perhaps we understand, or perhaps we don't. In other words, this mechanical property or any other properties, how do we know what determines that? And what can we do to change your structure so that your property is better? And also, can we change the structure during the process I'm making my product? So this is typically a relationship that we are working very hard to establish. I call it PSP. Usually it's very difficult. We usually maybe just do PS or SP, almost never PSP. So where does rheology fit? Well, rheology, I will go into great details about it. It's about finding some ways that can guide us making our polymers through processing. So I could be making this cover, I could be making this container, I could be making this fork, so some kind of injection molding. Basically, I need to imagine my polymer is in this liquid state so that I can change its shape and squeeze into different conditions and different shapes and end up having different products. This liquid state is typically what we deal with, called melt rheology. So it turns out that if we understand a little better on how this took place, one could actually find out it can affect your structure. And if you can manipulate the structure, perhaps you can achieve better properties. And more than that, you find when you use your polymers, for example, this is a polypropylene. Its TG is about minus 5 to 10. TG is something you heard about already, right? So it's basically below. So if you put it in the freezer, minus 20, it's glassy. It's very, very brittle, very rigid now. So when I take that out of the freezer, actually I can break it. That's how I did. But once you go back to room temperature, which is above TG, it's no longer so glassy. It's not glassy, and therefore it's not brittle anymore. But still, there's failure, and you can see that this dictates how strong the material is in presence of cuts. So that would be a subject further belong to the area of so-called fracture mechanics. So it turns out that my whole career has been devoted to establishing some perhaps universal and some good understanding in each of the three areas, and they are connected through the understanding of a PSP. I will have almost no time at all today, just because I was only allocated this much time, to talk about the fascinating issue of our AND property, right? The AND solid polymer. So for example, I have in front of me a polystyrene fork. And you perhaps know polystyrene enough to know it's brittle. Why? So if this is made of PET, I don't have my PET, your water bottle, or high-density polyethylene, it will not be brittle, or for different reasons. So unfortunately, I won't have time to tell you what we think are the ways to understand why styrene is brittle. This belongs to the subject of tool, and eventual fracture belong to the subject, sometimes misunderstood to belong to the subject of fracture mechanics, number 3. So today we are going to just focus on male rheology. It's very useful. It turns out a good understanding of male rheology is absolutely necessary if you are to make fruitful progress on the other 2 areas. So in short, I kind of summarize it similarly that this what I'm interested, which is a part of polymer science or polymer physics, has really 3 parts. The liquid state, where we deal with rheology today. And when you cool your polymer down, it either becomes glassy or semi-crystalline, such as polystyrene being glassy and polyethylene being semi-crystalline. And whether they are strong enough is the subject of molecular mechanics. And furthermore, if you have cracks, then you may have to deal with fracture mechanics. So these are what's in my mind very clear 3 episodes that we're in the middle of still actively involved in developing it. Just to give you a quick sense before we move on to rheology, is this example that perhaps shows the success of understanding rheology and even understanding what is molecular, in order to understand the molecular mechanics. So this is PLA, which is designed to be strong, ductile, and also contain enough crystallinity such that this PLA, whose TG is only 60 degrees. So normally, if you take a commercial PLA, which is polylactic acid, if you take a commercial cup, you pour water, the cup will just immediately collapse because TG is 60 degrees, water is 100. So this one was designed and developed due to our understanding of rheology to show properties that it's transparent. Look, this semi-crystalline polymer is not transparent because of the so-called sphere light, or the crystals are too big not to scatter light, so the light cannot go through. And this one is designed to contain crystals that are small enough so it doesn't scatter light and provide the rigidity and also remains completely ductile, unlike these brittle polymers. So that's really is a very fast snapshot of what's going on with the 3 topics. So today we will just focus on rheology. Of course, 3 hours is not quite enough for any of you folks. I know some of you are working in company. Let me just say up front, whatever we're going to do in 3 hours is a overambitious task of covering what is in this book, which is over nearly 500 pages. I'm using this 3 hours as an opportunity to summarize the leading features that we encounter in Rheology, and also at a more superficial level, how we sort of understand it. And perhaps I will talk very little about that, especially if the time constraint imposes so. However, this subject that's so useful for processing has been dealt with last semester in a full 3-credit courses, which has been recorded and uploaded to YouTube, actually. So actually, it's available in its entirety for us to take a look at. So if any part very brief, in fact, there are places to go back to YouTube to find. But I will try to give you a flavor in 3 hours, and in the intermission, if desired, we can go up and take a look at the instruments as a break, if you wish. But let me start by saying that so much of this I will just use for a while. Use a few slides in the play mode. So the polymers are still, its usage is still growing, and I see I have issues about finding my mouse. What do I do? Get rid of? I don't see it, huh? So let's sometime not use the play mode then. So this is, for example, a sense of several story height to blow plastic films, such as this one. There are annoying issues when you try to blow films. For example, when you this is just mimicking that. When you extrude your polymers through a die, in the film case, it's an annular die, but it doesn't matter. Basically, you find the extruded misbehave. It doesn't come out smoothly. So people spend millions of dollars to fix this problem. Well, if you can understand why that happens in terms of the physics, perhaps we could find better solutions or more effective solutions for this. Of course, this is the one extreme. It affects how we make our polymers more efficiently. For example, this only occurs when you are in a hurry, try to push your material out very fast. If you have the patience of pushing it more slowly, of course, then you are not making as much of your film, whatever, per unit time as you wish. So your profit will go down. So this is a side where people spend lots of money to add some additives to remove this behavior. And of course, on the other extreme side is how that applied, or that feature that costs us millions, could be understood and through computer simulations. So there's a wide range of topics if we were to really understand polymer rheology. I choose the title because in the past 15 years, a rather different view has emerged. So today, this is what I'm going to try to share with you. So one of the particularly striking feature was the way you mimic processing by trying to so-called shear it. I will say in more detail later. and then you stop shearing and hold it, you find your sample is not quiescent. And this is mind-boggling, never known 15 years ago until. And it really speaks a lot about the essence of this new worldview of polymer rheology. So let's go back to what it is. This several hundred billion pounds, and I'm always very eager to discuss this because this is a large volume, right? Several hundred billion pounds. But most of them really look just like this picture, which is an image of a ball of a crystal noodle. There are chances, if you magnify your polymer 1,000,000 times, it will look like this. They insert into each other, engaged in some very complex manner, in a many-body fashion, that no physicist claim to know how to handle it properly. Not today. Not when you can send your spaceship to Mars, but we don't know how to solve this problem. This means opportunities and challenges. And it also gives us a difficulty to determine whether this new worldview is all entirely correct versus the old view. I don't know how much I will say it, but let me just give you a sense of it. So in any case, all your polymer will look like this. It's really a big mess. We are trying to figure out how this thing behaves when you're trying to process it. There's nothing simpler to do processing. You know, this is squeezing and things moving. It's rather complicated. There's nothing simpler than imagining your sample being this orange, being sheared, so-called. And in rheology, which is the subject of learning how processing takes place to make this, it turns out it all boils down to how the sample changes its shape. So this shear case is, again, a shape change. It was initially rectangular, and it's being sheared and tilted. And you can define how much shape change occurs rather rigorously. You can define also how fast you are making this shape change. It can all be done, and I will try to say more with paper and pen, you know, blackboard style. So in any case, you can define this, and then you go to, this is abstract, you can actually go to rheometer, that which I can show you, and you find that you can put the sample in between two plates and have one of the surface rotate, and the sample is then being sheared. It's a torsional shear, but locally it's like a linear shear. And you can also try to shear it back and forth. And that's called oscillatory shear or large amplitude, depending on the amplitude. Or you can just make a step strand, which is the first movie I showed you, where you just move your surface a little bit relative to the height and stop there. So it turns out these three modes are all that you can think of in the case of shear about how you are changing the shape. You're either continuously changing it, or you're stepwise changing it, or you change it back and forth. That's all. And then that's shear. There's another way called extension. The time, I live in a good time when we were working on shear and find the need to go beyond shear to do so-called extension, which is a much more intuitive thing to do. You stretch. At that time, a local guy from Goodyear just invented a way that you can put this fixture on a rotating shear device and achieve the purpose of extension. By having this rod rotating, bringing two opposingly rotating a cylinder on which you fix your sample on. So that's extension in its simplest form. In your processing, your material either suffer this shear or extension or a mixture of both. But that's all there is. So in simplicity, we will try to isolate, look at the shear separately from extension. If you have a hope, if you can understand each case, you have the hope of understanding any more complicated case, which is a combination. So this will be a real sample, actually. I will show you more later when you are wrap it around two drum or two cylinder and draw it. Lastly, I mentioned about shear and mentioned about extension. The ones that really is in processing is mimicked by this. It's mimicked
so
by this so-called capillary.
Yeah. So we have our pressure
extrusion.
Gauge and the actual.
So here in the lab we mimic it.
What we're going to do is we're going to run some polyethylene.
I know we don't have the voice here, but basically, actually, this video is supposed to be talking. My student Travis is showing you a capillary.
We're going to load this in
rheometer. You
to
put
the bottom part.
A dye in here, and then there's this reservoir in which you
loaded a few pellets inside.
Store your material
what I'm doing
and use a piston to mimic the process of
I'm going to lower the pressure a little.
Twin screw or single screw extruder pushing material out through this little narrow channel, or you call it a die. The very first movie showing the so-called periodic roughness, we call shark skin, is what's coming out of that. Okay, here comes how this material he uses was pushed through a circular opening, mimicking processing, mimicking the way we made this fork, for example. So with that, I think I covered everything there is to do in our lab that we can design to mimic what we encounter in processing in the simplest way possible. Any questions? Okay. So I'm good. There's a lot of history, so let me see if I should at this point pause and say a few things. I will just go back and forth between several documents. The subject has a long history, so if you survey it, you'll find there are 32 books on the topic of rheology, and much of it is on the topic of polymerology. So I will call your attention to, just bring you to speed, to two books. One will be my book. The other is published in the same year as a second edition, after some 12 years, re-edition. And my book is called Nonlinear Polymerology, which is what you are dealing with in processing, because in processing, nobody have the patience try to squeeze and extrude the material so slowly that nothing bad happens, because you are not, it will cost you 10 times as much to make a bottle if you do that. So you are necessarily trying to push your material out as fast as possible. It turns out in that case, things become nonlinear, which I will explain in detail. And this nonlinear world of polymerology is something we began to know a lot more since about 15 years ago. Prior to that, very few books can really say a great deal about this nonlinear aspect. Since we are moving on to a few years ago, there's a great deal. In fact, my book have already been published. By that time, has already been published. Much of the essential work have been done. So this book is also able to talk about nonlinear aspect, spanning about nearly quite a significant space talking about nonlinear art. It claims to give you a state of art description, okay, and claims to be a fair summary of the progress that has been made up to that point. So I just want to, without any unnecessary comment, I just want you, if you have one day the interest, to grab this book and compare the content of that book to the book on which I base my lecture on. So, for example, I speak about, in the introduction, concepts such as yielding, you will hear them further, chain disentanglement, finite cohesion, which is really a new language in which we discuss the topic. A language you will find none in the other book published at the same time. Looking back, I look at how I concluded in the concluding page of the book. It says, examines available phenomenology, the reader may also benefit from forgetting about what they learned from the establishment, which is the Tube model. So let's suppose that there are no molecular understanding of the phenomenology, and ask how would we proceed and make sense out of the experimental observations reported in the book. So I further suggest that really the reader is in control of this mental exercise. Intellectual honesty shall guide us where we will end up being. Okay? So, in short, there are currently, I think you should feel privileged to hear that currently there are basically two parallel universes, nearly orthogonal to each other, as to what happens in polymer rheology, as to what happens in processing, which involves several 100 billion pounds of polymers every year. So I could only tell you what I think is happening, and I have probably very little time telling you how I reject the other viewpoint. But that's not going to be something that I'm obliged to do. In other words, to tell you which one is right. Obviously, if I don't think I'm right, I wouldn't be standing here talking about it. So the purpose of the next few hours is for me to essentially summarize, bring you to today's understanding about polymerology using 8 different leading examples of basically what the key polymer rheology is about. So I have this essential phenomenology printed on this hard copy, so I will just going to go through this so that you could start to become aware of the what you encounter generally in polymerology. So with that, I will start with from definitions. I think you will be at some point amused to know that the new phenomenology we find even calls you to modify the definition of the term rheology. It turns out if you look at any standard definition, of course, rheology is about understanding the state of deformation of your material. The state of deformation, however, according to textbooks, is actually assumed to be known already. So the thing you learn from rheology is actually just to learn in terms of the mechanical response. In other words, if I start to change shape in the case of shear, my concern seems to be to find out how much force I need to exert on the upper surface so that I can achieve this shape change. As for the state of the deformation, it's going to be shear like this, homogeneous. This is the textbook. So this textbook goes back all the way to nearly a century ago, the first paper that essentially prescribes, hey, you know what you're dealing with. You know how the shape changes. The shape changes this, uniformly. In other words, if my top plate has gone to there, my bottom plate sits here, then at half height, it will be just moved halfway. Homogeneous, okay? So the first paper would show you that. The subsequent textbook, this is 2007, will say the same thing. 2008, the book, mathematically, not pictorially, says exactly the same thing again. So it turns out this idea of homogeneous shear indeed works when the shape change is very little. For example, you don't move a lot to the left or to the right in your screen. Then indeed the sample will typically shear homogeneously. And you can do a variety of things. You can make a step shear and watch how much force results from this shear and whether that force declines as a function of time. If it's a liquid, it turns out that force will decline continuously until it reaches zero. And you can also move this upper plate back and forth. And this is a movie that shows that process where you basically interrogate your sample at different frequencies. You can see now it's not going back and forth as fast as before. So your instrument can allow you to probe the rheological characteristics of your material by moving back and forth and sensing the force produced by this back and forth moving. You can figure out something about your material, basically. A lot of details I'm omitting here because this is the rather trivial part of rheology where the shear is homogeneous and response is linear response. Okay, so let's get to some of the beginning of, I call it ABC of rheology, but really it's something that was hardly ever properly dealt with as explicitly as it should be. So I know for you this may not be such a familiar thing, so let me keep repeating the same thing. You put your sample, which now looks grayish, and you're trying to change its shape in shear. So the way to do it is you can just move your upper plate, and you can even ask yourself how long it takes to make a shape change of 100%. What that means is if your sample has a thickness of h, you just move 1 h to the right. That's a sizable, appreciable amount of shape change. We call it 100% shape change or shear. And depending on how fast you're doing it by moving the upper plate, you know exactly how much time it takes to make that shape change. It's given by this, right? Because you know it traveled h, and you use velocity v's, and obviously this is how much time it takes to make that shape change, right? This is something crucial. You, as experimentalists, have control on this T1, right? You know exactly how much time it takes, and you can control it because you know your h, and you can change your speed to alter this T1. What's good about that? Or why we concern ourselves with this concept of T1? It's a sizable amount of shape change. It takes a time that you can control. And this time could be 1 second, could be 10 seconds, could be a fraction of a second, could be half an hour, could be anything, depending on your dear polymer, depending on your molecular weight, depending on your temperature. These are the two most important variables in your polymer science. This time is hardly meaningful because it could be 1 second, it could be 10 minutes. It's the same as you telling me, I run very fast. I says, I'm not so sure. And the only way you can claim you run very fast, let's say 100 meter or 400 meter, a mile, whatever distance you want, when you say when you run very fast, you are not being precise. So how do you say that very precisely then? Well, you can say, it takes me about twice as much time as the world record. Now we are speaking. Now I know exactly how fast you are, since the world record is published. So this T1, again, is meaningless, has no meaning unless you compare the time with something else. And that's something else I'm aware that is not something that I will spend a great deal of time on because it's technicality. Today, I just want you to have just a pictorial, very, very non-quantitative verbal understanding of what's going on. So it turns out this T1 need to be compared with some internal clock that your dear polymer has during processing. So what I'm holding in my hand is a piece of so-called polydimethyl siloxane. Its TG is minus 100, so it's very soft. It has no cross-linking. So if I leave it for a long while, it flows into a pancake because there is no cross-linking. But yet, because the molecular weight is rather high, despite the fact it's very liquid-like because its TG is 100, it still bounces from the table. So from this very bounce, actually, I have a sense. That the internal time scale is probably a fraction of a second. If the internal clock is, let's say, a millisecond, this will not bounce back. Because I know the contact time of this ball to the table is much longer than a millisecond. So it turns out the internal clock that we're speaking about is this. Take this noodle picture. Each of the chain is inserted into each other. And because of thermal agitation, well above TG, all the chains are actually moving at all times. So it's like a bucket of snakes, except the number of snakes is 10 to the, for example, this. 10 to the 15. That's 1,000 trillion. or not 15 would be a trillion. It would be a trillion, and it could be 1,000 trillion in here, or several hundred trillions of snakes in this little piece. And they are moving like this. And I just told you they are moving about a fraction of a second. And that's the internal clock we have. So this styrene, if you melt it to 120, 130, that internal clock probably is half a minute, or even longer if it's, let's say, 120 degrees. So this T1 is going to be measured against this internal clock. I will not do justice spending 3 hours talking about nonlinear rheology without at least mentioning to you there's such a thing ubiquitous in polymers called shear thinning. You've probably heard of it. I grow tired of hearing about it. It is a concept involving steady shear. If somehow you manage to shear the sample forever, there will be a point where the force required to shear no longer change with time. So that's a steady state. And you will, as I will show you, you will be able to measure such a thing called viscosity. And then this viscosity, you find if you shear it faster, it will be smaller. And that's called shear thinning. Very well known for all polymers. All your 100 billion pounds of polymer will do that. The viscosity, which is how easy it flows, only start to drop when the rate of shear is sufficiently long. And it turns out, as you can see here, it turns out that this T1 is nothing but 1 over the shear rate, or T1 is nothing but V, H over V, or shear rate is V over H, which again you can control. So it turns out this is the point where the time it takes is just about the reciprocal, it's just about the same time as the internal time scale. Okay? So this is the time T1 is about your same as your internal time scale. If you change your shape very fast, much faster, you're on this side of it, then it turns out in steady state your shear rate, your viscosity will be much faster, much smaller, therefore. Okay? So, this this example just orients you about the consequence of shearing fast or not. So if you make 100% deformation, it takes a time much shorter than the internal time scale, tau. Then it turns out you have ability to cause your polymer to basically move much more readily. It is not the most significant point about polymer rheology, but it is a point where I can speak about the effect of fast shear. So let's get back to patiently enough. I know this is, let's see. I know this is probably better to do with animation. Don't be bored of it. We do it again. You shear the sample to the right, and the shape change is described by just how much you are moving to the right, which is same as saying the gamma is keep increasing with t. And the thing that if you never heard of before, you hear it here for the first time, that's fine. There's such a thing as a liquid. Liquid is such a thing where you'll find as soon as you start to shear it, the force you need to maintain that shear will be of a finite value immediately. This is known as Newton's law. Have you guys heard of Newton's law before? In this manner? Well, if not, be my guest. If this is the first time, it's perfectly fine. Basically, I'm going to change my shape in the form of shear. And I find that if I move my upper plate with velocity v over a height of h, okay, then I find if I double my velocity, the resulting force that I have to apply on my hand, upper surface, will also double. So that's linear response. So that's all given here. If you double v, you will double the stress. And the stress is simply defined as a force per unit area. The remarkable law of Newtonian fluid is that as soon as you start to move your upper plate, you will encounter a force here. You will not encounter a force of 0. The force will automatically be there just because you have already generated a rate of shear, because this is just the slope of the displacement. This is nothing but displacement over h. And at any moment, this is your displacement, which just keep increasing linearly. Notice what I have said it several times. We assume it's homogeneous. So at half a height, it will move half x. At a third of the h, it will move a third, or quarter rather. It's more like a quarter. It will move a quarter, and 3/4 of h, it will move 3/4 of x. So it's a linear, homogeneous. We automatically assume this to be true. Imagine this is not true. We'll be in trouble. In fact, so indeed we have this out of necessity, not just out of convenience. Because what? Because I have my sample only listen to me through this two surface. Nowhere else my sample can hear me. Yeah? The sample adheres to my surface. I'm holding the surface, either one. I have control of whether my surface moves or not. Anywhere else, this sample has no clue about what they should do. Clear? That's very clear. It turns out this is completely obvious. So, since you don't know what the interior will do, you assume it will do what I said. So a lot of this is highly elementary in that sense. And when it's elementary, you also have a chance to ask whether it's correct or not. So we'll get to that. For the moment, let's assume for simplicity this is what happens. And if this black box that you're examining is a liquid, I said the stress will immediately be of a finite value anytime when you started to do it. Well, there is a contemporary of Newton by the name of Hooke. He was studying solid, and he found for solids, if I have changed my shape twice as big, then the force that arises will double. So for solid, I don't speak about how fast I change my shape. I simply speak about the degree of shape change. In the beginning, since I don't have lightning speed, in the beginning, by definition, there is no shape change. Therefore, there is no stress. In other words, the stress could only gradually go from 0 and build up. So that's a solid. So you see how contrasting this two type of material is. Your dear polymer is neither of the two. Your dear polymer is this one. That, let me briefly say, that on short time scales, it's rubbery, clearly. And on very long time scales, it may be liquid-like if you give enough time. So I gently drawing this, treating it as if it's a liquid. And it almost is, because when I release it, it doesn't snap back. So your polymer, just remember this word, your polymer actually is viscoelastic. In other words, it has the duality of both being liquid-like and solid-like. And I will change this word as I finish my discussion to something else. In other words, it turns out this is used millions of times every day for all materials. It turns out materials that are deviating from these two ideal cases are all known to be viscoelastic. And I will almost I'm almost certain, without any making mistakes, that we should never call them viscoelastic. We should always call them elastoviscous. Why? Because it turns out all viscoelastic material, when you put it in between the parallel plate and start to shear it, it almost always does what I just draw here. Stress starts from 0. Therefore, its initial behavior is always solid-like. If we manage to shear until the stress no longer changes, you get so-called steady state. Almost never the other way around. For the universe that we know of, for almost anything on Earth, which remains highly fascinating to say the least, take a note of that. So it's really elastoviscous, not viscoelastic. So I have no idea who first called it viscoelastic. Perhaps it's by the very big giant in the field by the name of Maxwell, who had a Maxwell model, which I will have no time to go through. By the way, this book is available from the library, so you can have a PDF copy anytime you want. And the first chapter or two will speak about this elementary part of it as well, about Maxwell model, for example, I just mentioned. So it turns out your dear polymer always does what I just showed you. Your question becomes, when you put a polymer in between, does this happen or does that happen? In other words, how do you connect from the initial behavior to the final behavior? Does it smoothly just do what this white line does? Or your sample simply march on the dashed line and never reach a steady point? It turns out this is inconceivable, the dashed line. Whereas this behavior, it turns out, is possible when you change your shape very gently. So this is possible. And in that limit, actually, you have so-called linear response. Perhaps I will say a little more very soon. So in general, you have this. This is what you generally see. This is the essence of everything about nonlinear polymerology. It is one of the topics we will go through in great detail. So I don't need to spend more time on this at this point. But if I give you a quiz, you probably would not hesitate and say, oh, there are only two possible ways to connect this red point to that red line, either the white one or this other one. Okay. With that, I come to this list once again. So we're going to go through all aspects of rheology that we must understand to do better processing. We must understand to manipulate the structure better to achieve better properties, as I showed you in the example of that PLA cup. So we're going to go through all of them. The first one is first, because I'm eager to at least indicate what is linear response. So in other words, what is the rest, which is nonlinear. So, let's move on. Let's move on in two ways. First thing first, let me say, I think the red color is good enough, but I could change to a different one. Let me say a few words about linear response. Gosh. So you have seen two examples of linear response. Newton's law, it says, it basically says if you double the rate, you double the force applied. So the relation between them is linear. And then Hooking's law is the same. It says if you double the shape change, the force it requires also should double. So the relation between them is linear. So this, because of that, we call them linear response. The unfortunate thing is, or the complexity we're facing is our polymers, the way you are in a hurry trying to process them, does not obey this linearity. So it tends to be nonlinear. What can be a better way to say about the nonlinearity than what we already did? That this dashed line will be linearity. It cannot happen. This flat line will be linearity for liquid, but our polymer is not just a liquid. So it's pretty clear linearity is a very limiting view. Just let me say one more time. This not possible should be quite clear to you. I don't think you know of any solid that you can just keep changing it, for example, draw it without breaking, without seeing it breaking apart. It never happens. Yes. So I know that's the question. For the last 20 minutes and for the rest of 2 hours, we are only dealing with liquid. In other words, your polymers is above TG, above TM. There's no crystallization. There's no glassy state. It's all in this so-called melt state. So I know where it comes from. So the story. This poor polystyrene, it obeys Hooking's law up to just a few percent, beyond which it already breaks. Oh, there is something you learned, which means since you are forcing me to say a word about, shall I say, the connectivity. You have your dear polymer. Above TGTM, it's all in this, gooey, this kind of gummy state. We call it rubbery state, you may call it. And then below it, it's rigid and so on and so forth. So I think, indeed, you guys should feel free to think about both of these two states. Of course, being aware that we're going to be dealing with only this gummy rubbery state. What I'm trying to say is the following. The language is the same. What language? Shape change. What language? The force that arises from resisting to the deformation. Those will never be different. It's all going to be called stress. It's all going to be called shape change. What is quite obvious, I see why you have that question. What is quite obvious is when I cool my polystyrene to the glassy state, treating that as a hooking solid, sure I know I couldn't cause it to march along the dash line. Something else happens. And obviously something very disastrously nonlinear happened. It breaks, actually. But why you guys are forcing me to think about this uncross-linked rubbery PMMA or any polymer when you're trying to do processing? Intermission, you can pass and feel it. Any polymer, you do several hundred billion pounds of polymer processing, they are literally in this state. If it's polyethylene, I don't want to examine that state with my finger because that will be done at 140 degrees, I will burn my finger. But otherwise, this is your polyethylene. This is your polystyrene. This is all your polymer will look like this. So it is indeed very odd, or people just cannot wrap their mind around. It is indeed very odd to treat this thing as solid. But I just said very, very strongly to you, this thing initially does behave like a solid, without exception. Certainly for your dear polymers, let alone your steel or some other viscoelastic material. What's remarkable is whether it breaks or not. In other words, this dash line may not continue, but it doesn't mean it breaks, right? That's why you're asking whether I'm talking about above TG or below TG. Even if it's rubbery, this line doesn't continue. As I said, it continues to this red line. It bends over. But that bends over is a clear indication indication of something highly nonlinear. Because all we know in terms of linearity is these two forms. In fact, viscoelastic material can be written even in this linear form. I can give you a example of so-called, I know I'm drifting a little bit. If you do oscillatory shear, it turns out there is a region your polymer can be linear. In other words, how much you deform will produce a force in proportion. So there is a boring linear response region. But let's just look at the reality. The reality is typically when you put something in between your polymers. There is the obvious limit, it turns out, not so obvious to you perhaps, but it turns out that there's something obvious if you look at the stress as function of time or displacement. There is a limit where this thing will change from elastic to viscous or flow. That's in the limit when the time to make 100% deformation is very long compared to internal time scales. The opposite limit is where we're concerned in processing. When you try to shape change your sample very fast, such that to make 100% deformation will take you a negligible amount of time compared to the internal clock. Then you are giving your chains no time to move around. That's the essential concept. The chains have no time to move around when you make 100% deformation. In other words, 1h to the right, for example. In fact, your tau could be 1,000 times larger than T1, which means you can move 1,000 h to the right. The chains hasn't had a chance to move through diffusion, through the so-called, we all know this concept, right? The above TG, the molecule move around. That's called diffusion. And because of that, there is a time internal clock. That limit where you can make very big shape change without the molecule having any ability to voluntarily move on its own, is the limit of processing, is the limit that that most interesting thing occurs, and is the limit we're interested in dealing with. And what you find is your stress simply grows from 0 and builds, instead of following the dashed line, it follows the white line. Okay? Man. Casually, for many decades, 6 decades at least, we call that, who have trouble with that? We call that overshoot. Sure. But nobody called that yield point. There is a brief moment in history, Professor Bryce Maxwell from Princeton briefly called this yield point, and nobody paid attention to what he said. And people forgot what he said. And that knowledge never even passed on to me, so I didn't know this is called yield point until we were forced to think and realize this is the yield point. By the way, speaking about connecting the different world, when you cool your polymer to the glassy state or semi-crystalline state or whatnot in the solid state, when you examine its mechanics, the same white curve might occur. It turns out. When it does, you call your material ductile versus brittle. This doesn't occur. So if you have your polystyrene, yes, you march along this line. The poor guy just break here. And if you have your polycarbonate or PET, the water bottle, it will show in the form of the white curve. Okay, here. There is a catch. In your polycarbonate or PET bottle, this point takes place. I hate to use time here because time is not a variable we have. You talk about shape change. And it turns out solid is so difficult to do shear. We don't typically do shear. We just stretch, so-called yin strong. We stretch. So when we stretch, we just say, oh, this is my original length. I'm going to stretch and see how much longer it becomes. Okay? It turns out your PET, for example, it comes about just 6% when it starts to yield. Not to confuse you, if you talk about your polymer in the melt state above TGTM, this point typically could be 3. Or just using the same common language, L over L0 as stretching. Again, this point could be 3 or more. In other words, you could triple your length before you reach that point. Whereas in the solid state, you reach the same point, but only 6% of length change. But man, other than this quantitative difference, which it's because of the different physics, we'll talk about the rheology physics, where we will not talk about the glassy one because of the short of time. But other than this difference, qualitatively, what else is there to say? There's a maximum. It's the same thing. So in the solid state mechanics, of course, people call this the yield point. And today, of course, we call what we observe rheologically this point the yield point. And if you check dictionary, my God, we all do, Google it, you find yield, oh, it's a term in engineering typically. It represents a transition from elastic deformation to plastic deformation, or to something irrecoverable, or to flow. So essentially, it's the termination of elastic deformation. That point is called yield. Okay. This concept remains difficult. All polymer rheologists, nearly all, either refuse to call this yield point or accept the meaning behind the concept of yield point. I can say for a long time about what's going on here, but we don't have the time. I could I'm, as you can tell, I'm essentially speechless. 15 years ago, if you ask me, not 15, maybe 20 years ago, if you ask me, to be precise, just 20 years ago, if you ask me, what is that point? Because that point has been known for 6 decades. That if you put your dear polymer between parallel plate and you shear and you monitor the force, you find the force reach a maximum and then crashes down. It's known for many decades. But 20 years ago, if you ask me what is that point, I won't be able to tell you it's a yield point. Silly me. Because you just go to the dictionary, you will necessarily force yourself to say that is a yield point. Because the material ceases to exhibit elastic deformation. Why? Well, it goes back to why you have elastic deformation. Well, you have elastic deformation because there is a structure that's elastic. Oh, I know, I'm mouthful, I'm speaking. We have yet to talk about what that structure is. In fact, today I'm not prepared to talk a great deal about what is that structure to you, because I'm trying to stay at a somewhat superficial level. But you know rubber elasticity, right? You know cross-link, so-called concept of cross-linking, right? So you can have a pre-made polymer. You introduce some peroxide and you react, or in your rubber case, you use sulfur to cross-link it. Basically, you can fix a few points. All of a sudden, your polymer become solid-like, or indeed solid. The cross-linking made sure that the chains can no longer move. And anytime in our mind, we should feel free to have a picture of what is that elastic structure is. It's this. If you have cross-linking, of course, this network, nothing you can do about it. This is your structure. The structure is a chain network, if you like. That's the structure. They can elastically stretch it. And of course, you can even rupture your cross-linked rubber, experiencing considerable non-elasticity because it catastrophically failed, because some of your chains has to undergo scission, enough of them such that a fracture surface occurs. So what is our structure, PDMS, on crosslink? Well, our structure, which I'm going to say it once, and that's all we're going to do, is our structure arises rather similarly to cross-linking because of these points arising from uncrossability. When the chains are very long, they intertwine into each other, impossible for them to break each other in order to switch. They cannot switch because, look, I can switch here because if I'm near the chain end. But if this chain is going forever, there's no way to switch. And if there's not enough force to break it, this forms the junction. This forms the topological constraint that at least leaves temporarily. In other words, if you have the patience waiting, this chain may eventually go out on either side. But of course, your chain is typically much longer, so this thing continues on this side and make all kinds of loops. But let's pretend this is the end. Then it may try to move out eventually. That gives you the internal time scale, and I just talked about the fact that time scale may be very sluggish, very long. Meanwhile, you are trying to smash and try to shape change it. So this structure will respond elastically just like a cross-link sample, and the structure is coming from uncrossability. Okay? That's very elementary. Nobody knows how to describe this hundreds of trillions of chains together doing all this, forming a network. But I think it's not controversial to agree that this should be how to perceive it. And if you do, the arrival of this point is clearly a point somehow this network coming from uncrossability is forced to break apart somehow. Otherwise, you should continue to stretch as if you're stretching a piece of cross-linked rubber. I must say, I'll be disappointed, let's say this way, I'll be disappointed if you don't follow what I'm saying here. But I think it's sufficiently simple you do. However, the mainstream of polymer rheology has yet to agree this is how simple it is. That's fine for me. So in any case, this is what you see. It's up to each of us to interpret what it is, and there are sophisticated ways to interpret, as I tried, showing you that this yield is what? Yield is associated with some structure falling apart. Falling apart either voluntarily, you see, when you are trying to do it so slowly, this yielding can occur voluntarily by diffusion, by the snakes all moving out of each other, so-called reptation. I apologize for not giving you all the terminology and the concept behind it. Basically, these chains are like snakes. They raptate, so-called, according to the famous Dejeuner. And so they can get each other out of each other's way and reform and achieve this yielding in an unforced manner. Nevertheless, it's still yielding. The state here is not the state here anymore because they have rearranged through diffusion. And when you do it with fast rate, that's a bad case. You are going to force the structure to break apart, perhaps. In general, we know that this is a yield quite trivially. It turns out you can shear your material, and you stop shearing before reaching maximum, and you let go. Let go means you have stress-free. Release your upper surface. It tends to snap back completely. Okay? And conversely, when you are on the other side, it tends not to do that. I know it's a bit slow here. So basically, it comes, in one case, it comes back. In the other case, it doesn't. Okay. So with all of that concept in mind, I can speak about the first topic. I know an hour has passed already. I may have to speed up. But generally speaking, let's talk about the first one, linear response. So the deformation and the force are linearly related. So that's called linear response. I give you an example of stress versus in extension. What did I do? So I should apologize for you. Usually, when we do shear, we have this constant as G, not E. I apologize for actually going so fast. We call this viscosity, and this G in front of this gamma has also a name called modulus. It is a measure of how stiff your material is. When you have a linear response, so it turns out you can think about extension. So your sample become a little longer. This is our original length. Now it becomes slightly longer. And that's L over L0, L minus L0. And you normalize by the original length. That's how much shape change there is. So if you do extension, this is linear in that, that's a linear response. The first topic of finite cohesion, I mentioned it. Because the established theory failed to accommodate this. So finite cohesion means it turns out such a relationship holds for this. This is the shape change, right? It's a little longer. How much longer? Well, you compare how much longer to the original length. So this is the change of the length and divided by the original length. We find that this is up to, let's say, 50%. In other words, instead of original length, you can go to 1.5 of the original length. You find up to that point, the relationship holds. Okay. It holds at all times. In other words, you can make such a deformation. You'll find this holds at all times. As long as this is smaller than 50%. Whereas the established theory, such as tube model, says this never holds for any change, for any amount of change. So I'm not going to go into a great deal of details on why. Basically, the point is, when this is true, it means there is a finite range for linear response. Which is important to indicate. So let me just go on to next one, which is overshoot. In fact, this is the one that we already talked about. So overshoot in startup shear indicates yielding. So that's the comment I want to make. I don't need to repeat this. Basically, the stress overshoots. And this point actually changes depending on how fast you are shearing it. So it turns out this point, for a weaker amount of shear, it will show up earlier. So there is a trend well established. So it's not a fixed point. The arrival of this yield point does depend on how fast you are shearing it. So this is in the direction of high shear, so which you can control because you are controlling the upper speed of your plate. Okay. So let's move on to the third one on my list, which is understanding of wall slip. It turns out I could just spend 1 hour talking about wall slip for you, because it is most unique for polymers. So it turns out, unlike many other materials, you know what's unique about polymer. There's one variable that's unique about polymer, which is what? That ceramic doesn't have, metal doesn't have. What is that variable? What we speak most about a polymer, if we say we want to vary something about it. You don't do that much with ceramics or metals. Once I fix the composition, well, it's the molecular weight. It is the most readily tunable parameter, and so, no, molecular weight. It could be this long, it could be this short, and it could be longer, and it's not something that that you possess that freedom in dealing with ceramics. So it's absolutely unique. So because the polymers we made are so long, by the way, you know why we're making them long? Not to shoot our own feet. Because when it is long, it's actually getting more viscous. Processing becomes more difficult. The kind of shark skin I just showed you is a result of having very long, very high molecular weight. Well, it's because if you don't have high molecular weight, I cannot even make a fork out of styrene. Okay? If this fork is made of styrene with a molecular weight of, let's say, 50,000, it will never have the strength that I'm having here to pick up anything. This PET bottle, polyethylene, again, still need a molecular weight of 100,000 or so to have adequate mechanical properties. So we need them to be necessarily long, turns out, for the final mechanics. So that's the beauty of rheology versus the rest of it. It turns out we all have to deal with high molecular weight system. And it turns out when there are principally, the problem is in rheology, because when they are very long, they get into each other in such a difficult way that they prevent each other from moving around, and the sample looks more elastic-like, turns out. That's probably not very difficult to imagine, because I told you the elasticity comes from their uncrossability, and uncrossability become more severe as the chain becomes longer. So it turns out a polymer exhibit such a thing called a wall slip, which I don't think we can really quite avoid it, talking about it, because partially because we have avoided talking about it. So what we did was we assumed that if this upper plate has velocity v, oops, then my polymer next to that wall also have velocity v. Not to have that is unimaginable. Because I told you we count on the two surfaces to dictate or to exert shape change. We already admitted we can exert shape change only through those two surfaces. We cannot ask the sample to listen to us and saying if velocity here, the velocity is v, at half height, it should be half v. We say that to the sample may or may not listen. I notice microphone on. Now you can hear me better. Okay, so the idea is you can see the sample no longer follow the moving surface, which is invisible on the top, and the bottom surface is now moving. And you can see at some point the sample also start to move on the bottom, which means the polymer is also not able to adhere to the bottom surface either. So you end up having a plug-like flow, where the whole thing just moves together almost. In other words, attending very little shear in the bulk. So what we could tell in terms of new phenomenology is to explain how it comes into being. In other words, how it has this no slip boundary condition, and at some point that condition is violated through this interfacial failure. And of course, having this means it changes the way you make measurement, meaning you thought you are imposing this shape change as you showed in the left, in reality, it's transcendently doing all sorts of things, and in steady state, it may do something as shown on the right. So this is all happening, this is real time, so it's all happening within a matter of only a few seconds. In a few seconds, it establishes this final state. And this severely affects the processing. So for example, the very movie I showed you about this shark skin, for example, this feature can be completely removed if you artificially induce this wall slip. So people pay millions of dollars to add some additives that goes to the surface of the die to encourage polymer desorption such that the sample remain permanently in a slip state, so that you no longer have this disasters called melt rupture, sometimes called. So this is a necessary part to understand in processing, which you can trace back to this aspect of elementary aspect of rheology, because you are talking about setting up a proper or reliable boundary condition, only through which you can confidently characterize what you are doing. The long story, the nature of wall slip eventually was understood, but it took a while. And I'm just emphasizing the part of having no wall slip to the point wall slip takes place. That physics can be actually properly understood. So I could move on to the next one. Let's go directly to the next one, which is, if I write it, follow the yes, go ahead.
Is that wall slip kind of help to explain the yield stress or the yield point?
Good point. No. Your mind is turning. Yes, this wall slip, especially the way I presented, that there was no wall slip to begin with, and then it occurs. It implies, okay, seems good point. So if you do that in simple shear, again, it doesn't matter you use the shape change or time. If you monitor this with the stress that you have, pretend somehow you could remove the slip. Turns out there is a way to do it. I'm not going to go into detail. So if there's no wall slip, it will do something like this. It turns out wall slip cut everything pretty much, as you can tell. It prevents you from building enough stress, so it may prematurely fail here, and in some more abrupt way like that. Yes, so I'm glad you mentioned yield. So if you call this yield, what is that? Well, without a movie, you may still call it yield, but in fact, there is a word I precisely use. You may call it interfacial yield. So it's exactly the same concept. In other words, so what failed? The structure failed. What structure? The structure of these red chains initially inserted into the white chains, and the moment they pulled out of the white chains, that is a structural change. So it is sound to call that as interfacial yielding. Oops. This just has to do with that, yeah. So, need the right amount, yeah. So, yes. So there is a abstract way of seeing it, but you have the movie, you know where it comes from, the source of it. This exactly gets you to the most worthwhile talking point, because it after all is the first discovery we had, which is so-called shear bending. We will spend a little more moments on this. The very fact whether this assumption is true or not. As I said, it was really even for me, I pray to God. Even though I don't go to church, I pray to God that this happens. In other words, that you have a homogeneous shear. Because if you have no control, if you cannot dictate, then we cannot make a measurement. So in other words, we have a shear rate, we assume this is way other, and this is only true if you have a homogeneous shear. So that I can use a single parameter to say that every layer I have is doing the same thing. Homogeneous shear at this rate. And the degree of shear, which is this, is the same. It tilted this amount here, it tilted also this amount here, it tilted also this amount here, right? Although it is only a millimeter, typically, in our lab, but in fact, in processing, indeed, this is the right scale. It's all the processing equipment we have. Almost without question, you are in the 1 millimeter to 10 millimeter range. So 1 millimeter is just perfectly fine to illustrate. But it happened to be 1 millimeter happened to be too small to visualize. So although it's only a millimeter, as I said, I think I already misspoken about 10 to the 9 is a billion, 10 to the 12 is a trillion, and then 10 to the 15 is already 1,000 trillion. There must be a name for it, right? So this, I never checked the dictionary to find. So this piece, you can back calculate, probably already have 10 to the 15 molecules, chance. So although it's a millimeter, you know the polymer typically is of the size of, let's say, 30 nanometers. For convenient, that's, easily you have 10,000 layers, because a millimeter is no, did I say? What did I say? So a millimeter is already 10 to the 6 nanometers. So each of them, even if R is 100 nanometer, that's 10,000. So there are 10,000 layers of chains. So 10,000 is a large number. And even though it's only 1 millimeter, the wish that you can ask every layer to do the same remains a wish. In the past, we simply assume polymer will behave properly. It will do what I showed you here in any textbook. This is under the condition that these chains are being highly sheared. So in other words, they have no time to swim, and you're trying to smash them and change shape. Can it happen? So there was some feeling. It took a while, right? There were a lot of background I have no time to go through. But it took a while for us to eventually become, to have asked the relevant question. You have a $100,000 machine, which enables you to do all this measurement. No commercial machine is equipped with this device, which only takes $300 to enable you to confirm that this is happening over a millimeter or not. Again, a millimeter is just too tiny for you to discern about anything. So you have to take your $100,000 machine and then on the fixture, dig a hole, put a piece of glass, send some light through. In your sample, you have to pregnant your sample with some light reflecting particles, 10 microns big. It doesn't have to be a fluorescent particle, just any particle that reflects light. And then you take your pointer, which is readily available 20 years ago already for $50. So you shine that little laser. You take an objective lens from microscope of 3x, which is $50. A CCD from civilians cameras, $50. So it's less than $300. You set up this. Only when the motivation comes. Somehow there's a way, there's some speculation by the time of, here it is, 2006 or so, that we may find something. And here's what you found. So this is textbook, convenience, necessity. It enables you to claim that I can go to a lab and conduct a reproducible, reliable, meaningful experiment only if this homogeneous shear is true. So once again, the device I showed you, $300 device, and the gap indeed is about 1 millimeter or so. And you don't see the upper surface because it's not illuminated. Only the sample is illuminated. And by the time I spoke, things already happened. So you can, it will repeat itself, but basically you can confirm initially the sample indeed does what textbook showed you. It homogeneously sheared, shape change. But you can see up to this point, it's being sheared very little and victimizing a portion of the sample being sheared much, much more. In other words, they ask certain portion, see, that's all sheared properly and then breaks. See that? In other words, all you have is two things. So I just mentioned about wall slip. So you must understand wall slip and suppress it. So we are speaking in absence of wall slip, which means your sample will either move with upper surface or lower surface. So let that be true. But in that limit, it doesn't mean everywhere follows this linearly, right? So what happens is the sample certainly is aware I need to adhere to the upper surface and the bottom surface. That they know, because I make sure that happens. There's no wall slip. We understand what is wall slip, so we know it. So we can make sure that doesn't happen. But then other than that, the sample is free to do anything they want. So they choose to victimize a portion of the sample to go try to catch up with what the upper surface is. The rest just stayed very little sheared. So now it's breaking. See how sharp that place breaks. And then this thing go nasty and swim, smack that back because there's elastic recoil going on. So then they manage to have much of the sample hardly sheared, only a portion of the sample trying to satisfy the upper speed of the plate. And you can confirm this for sample similar. It's all done to mimic this. And no matter how long you shear, there is a portion that's hardly sheared, the rest just gets sheared very much more. And you have no control how they will occur, other than the fact it occurs. So the movies of this, in fact, was the reason we called that overshoot. This all happens, this failure. I know the best presentation would be show you the movie and show you also how the stress is building. Basically, building to the maximum, only after reaching the maximum does the failure start to occur, the so-called shear banding start to occur. So it is this movie that made us realize, Jesus, however imaginative you want to think about the structure, at least just based on this millimeter scale, I see something falling apart. So it is that movie, like this one, that causes you to realize, oh, that maximum is a yield point because something is falling apart. It is the falling apart of that structure that made certain the stress cannot build up, right? So the stress coming down results from the fact that the structure is falling apart. Then, of course, you may go on and think about why they fall apart, what condition and the weak condition this can occur. And of course, that's what engaged us for over a decade before the book was written. There are, this is all today looks quite trivial. There are quite a few things involved here. First of all, I mentioned you should try to make sure it doesn't undergo wall slip. Secondly, it turns out commercial instrument, that anytime you can come to our lab to see it, is not built to handle things like this melt. And the reason it is unable to handle this is it turns out for a piece of melt, they never retain this nice shape. It will go so-called undergo edge fracture. The sample will start to fall apart from the free surface, the meniscus so-called, or free surface. We call it meniscus or edge. So the polymer has all kind of way to become nasty as a melt. And therefore, the rheometer builder says, I'm not going to produce one that you're never going to be able to use my rheometer for. So the rheometer we have commercially cannot handle melt in the sense it doesn't have enough force. It will break your machine if you do so. So with that as constraint, with the fact of so-called edge fracture, it turns out the way to visualize, unable to mimic what's going on, is to dilute, instead of taking this melt, you take this melt diluted with quote-unquote solvent or low molecular weight of the same polymer, such that it's much softer. So the stress response is adequate. So don't take this as an indication that this physics doesn't work for melts. I will show you result it does. But these movies are just built on some 15%. Even you can use, it turns out DNA is a very convenient substance to mimic this uncrossability, which we call it entanglement. So let's move on. It is this movie that we did first, and then for reasons that would take too long for me to go through, we start to look at a more benign case. In other words, we look at the case of a step shear. So this is, after a long story, realizing that step shear, which is a much simpler experiment, because what you do, right, you basically put your sample between your parallel plate. This is your sample. And you're going to do a stepwise shear, in the sense you're going to just displace it like that. So now your sample looks somewhat like this. In other words, let's say so I try to draw. So this is how much shape change you can imagine. It looks awkward because I'm drawing a linear shear case, but as I showed you, in the case of rheometry, it's a double disk, so it's a rotational. So the shear is continuous. There is no beginning, no end. So the sample is all connected. But this linear illustration is fine. Basically, sample initially started like this. It will be sheared and tilted. Let's say this is about this is H. This is about 1.5 to 2 H's to the right. So the sample will look like this now, right? Literally. So your sample will look like this now. And you hold it. So this was what you do. So you have a sample. And you know this looks funny because when you go to do an experiment, what you will try to do with a little bit of engineering is that your sample will be even in a case of linear shear, without rotation, will be much wider than the edge. Okay? So now you can appreciate a 200% shear is just like that. Nothing, right? In other words, the aspect ratio is very high. So you can indeed just move your upper plate 2 H's to the right and hold it. And now your sample is all just this. And your initial sample, of course, was this, right? Up to this. So you hold it. And by the time of the very beginning of 2006, we had the reason to do such a silly experiment. When I say silly, this experiment is almost infinitely easier than this experiment, which you have to shear a lot, and then you have to use a rotational device to shear it. This just move 2H to the right and hold. By the time of the spring of, or very beginning of, in fact, end of 2005, I realized that if you just do a step strand like this, something remarkable will happen. Something remarkable will happen that involving a notion that never existed prior to this experiment in rheology, which is we expect when you're holding it, there will be motion in absence of any ongoing deformations because you stopped. Okay, you stopped after 2 strands, 2 H's. You hold it. And we expect through the same movie, which we called particle tracking velocimetry, we can expect that your sample will not be motionless. So this is the one that truly changes our view about how to understand rheology. So this is exactly gently, because the internal time scales are half a minute. Therefore, to make 200%, to make 2 H's to the right, as long as I spend the time much less than half a minute, I'm shearing very fast. So it's like a step strand. Look at what happened. This turns out, not the initial one, but this subsequent one, involved indeed a melt, and involved indeed just a linear apparatus. Just build a, put 2 surfaces on a track with one surface driven by a motor. And so that, and with a gap small enough relative to this whole plate, which is much bigger, and just move 2 H's to the right and hold it. Again, dig a little window, shine laser through, and have a camera on the sidewall, which is also transparent to watch it. And this melt, if you don't treat it, it will undergo wall slip. So we actually conveniently use the super glue to glue it. This is SBR, which is commonly used in the tire industry. And it turns out it was nicely sheared to 200%, and it was nothing until 10 seconds later. Look at this, breaks apart in the middle. So if you shear a little too much, you will find by moving 4 H's to the right, you'll find this actually would occur this would occur even before you stop shearing. Look, it start to break already. So this is just all craziness, meaning prior to this point of 2006, everyone in the field thought after step shear, there will be nothing to be seen, meaning everything should be quiescent. Molecules will move. Even theory around molecule will be forced to move much faster because now you have deformed your chain. But it was all assumed that all the molecules will move uniformly such that there will be not a favored surface where the breaking occurs there. So the movie clearly shows there is a place where that surface just break apart and releasing the elastic deformation, so the deformation retracts back. And as far as we can tell, this was just a horse race because it involved 10,000s of layers, or 100,000 possibly of layers. All the chains have the chance to undergo this failure, structural failure we call elastic yielding. It's just a matter of which one wins, meaning the ones that started first will win because all these 10,000 layers are connected. Once one layer starts to weaken, it can no longer hold the stress. That will be the place it accelerates the failure. So sequentially, that was how we eventually was able to go to the lab and demonstrate that this happens. And once we know that, we actually could start to even predict something. So this is item F on the agenda, on that list, that I call it a rested wall slip, which is really funny business. In other words, you could now understand the physics by the time. In fact, all the physics leading to this book was quickly understood by the time of the summer of 2006. The paper was written 2007, and it took another 11 years for the book to be written. There's just too many other things going on. So, but the physics was already understood to give you this prediction, which is this. You can take your sample. We already know what is wall slip. We know wall slip doesn't right away occur. And you can predict, if I keep shearing, I can move 2 H's to the right without seeing wall slip. But you predict, if you stop shearing before reaching 2 H's, you stop shearing 1.5 H's and stop, wall slip will take place. In other words, it will occur, it will be induced. The word one uses, yeah. So here's one. Look at that. So there was no wall slip during shear, but it's the termination of shear that induces the slip or the failure at the surface. Once it fails, you see, all that deformation was elastically imposed. So the failure allowed the elastic deformation to recover toward the beginning state. So this movie is, so it's the same thing. We have to do it for several samples just to convince yourself this can. Indeed, it's very difficult experiment because you have to really have your sample adhere to the surface so well that it resists any wall slip until you induce it. Yeah, so this one, because the molecular weight is high, you can clearly see a delay. You can call that a delayed slip. You see, it's delayed. This is obviously counterintuitive. In other words, you would never be foolish enough to even look for it. In fact, it was first understood that this must happen that we went to the lab to look for it. There are other similar, I see similar things that to follow, which I remember mentioning to you, that you can see all this actually was done in shear. So by this point, we realize this physics that happens in shear is not unique to shear. So this is the shear, this is the movie that I'm showing you again. After 10 seconds, it will break up. And by the time of 2006, we clearly understand what was the physics for the shear banding as well as for this so-called non-quiescent relaxation. You can see, right? It breaks apart in a shear scenario. This physics is understood to arise from subjecting this structure to too much deformation. If I have time at the end, I will try to describe a little bit of this molecular picture. So in any case, if this is the physics, we expect this physics to occur in extension. So that's when we learned our colleague in Goodyear was inventing this double cylinder. It's about the same time. So we immediately purchased such a fixture and put it on our rotational device and made this prediction that after stretching this filament and you hold that filament will break up for the same physics as in shear, where the supposedly quiescent relaxation did not prevail. Instead, you have breakup of the structure that give you the motion. And here, the breakup, of course, will give you a failure. Breakup of the structure. And that breakup presumably is also a horse race, meaning it could happen here, it could happen here. It just so happened, that it happens around here. It's not a point we can predict. In fact, I pointed it wrong place too already. So it's just somewhere along this filament that this can take place. So, here comes the bigger part of the story that I wish to spend the rest of the time talking about it, and before we go to the final, maybe the molecular picture of it. The physics of yielding. So let me use a few slides to talk about this. The physics of yielding, we have witnessed it through the observation of shear bending. So we find that at some point here, the samples start to break up. And so this movie was really give us all the insight, allowed us to realize that this is a point of failure. See, there are actually 2 points to this. I must emphasize this greatly. There's no question this is a yield point. That is pretty straightforward. What is not so straightforward is whether at this point you must have shear bending or not. In other words, you can have this yield point, which is the termination of the elastic deformation. So it's elastic on this side. It's a flow on this side, or non-elastic on this side, because some structure is falling apart. This falling apart occur in the form of shear bending. That's lovely. But does it have to happen? So that's the little deeper part of the story. I hate to say we were just being lucky, but you can use that word. But the essential point is this, that the sample we choose is such it's capable of shear bending, as you show here, as you see here. You could easily have, let's say, for the very same sample, let's say I choose a 5% solution. It will have the same overshoot. There will be no shear bending. had you only performed such an experiment, seeing no shear bending, you probably would still not have the insight that this is a structural breakdown. Although the structural breakdown, nevertheless, also happens there, also give it overshoot. In other words, the overshoot clearly is the indication of structural breakdown. It's yielding. But this structural breakdown can still happen sufficiently homogeneously throughout the sample, in which case it will not have a shear bending. This is a very convoluted way for me to say. In fact, the detail is this. It turns out if you are not sufficiently entangled, this is why I quiz you, the most important variable in polymer is so-called molecular weight. It is everything because we have to deal with having high molecular weight because all the strong, solid mechanical property require you to have high molecular weight. And the way to speak about that typically is to speak about a unit. So this is a unit that's called entanglement molecular weight, and it's all about how big this number is. In other words, your chain will be made of many of such units. Okay, right? That's quite clear. So, okay. I'm inviting you to think that when the chains insert into each other, you can define a unit where my chain will involve in one of the this uncrossability, and comes here, it will involve in another one, and come there, if I run out of color, it will involve yet another one, okay? So there are many of these units. The longer the chain is, per chain, there will be more of this unit coming from each chain. And this ratio, of course, depicts how long the chain is per se. The longer it is, the more massively they are involved in this uncrossability, which give rise to the chain network. So it just turns out, which is all, to me, fairly clearly demonstrated and possible to understand analytically. This ratio, indeed, that's okay. I'm not going to change it. Usually the computer tends to crash when you do that. So this ratio speaks everything about what? By the way, it's this ratio that dictates the internal clock. The larger the chain length is, the more massively longer the internal clock is. In fact, let me just say this. It's all in the book, so it's all for you. This internal clock grows with molecular weight, or this ratio, to the 3.4 power, which means every time you double your molecular weight, internal clock shoots up by a factor of 10. 2 to the 3.4 power is 10. So it quickly becomes massively sluggish, your sample, and massively viscous. It turns out, according to Maxwell's idea, the viscosity is exactly proportional to the relaxation time through the modulus. So what happens? I'm saying that I could have had a sample which are not as entangled. Then what happens is the following. When it turns out that this reaching this point is a point of so-called force imbalance. In other words, when I keep deforming this chain, I build a lot of tension here. Okay? I call it tension, but actually it's called a rubbery or entropic force in the strand. As I shear more, this force builds up more. So what balances this force? Well, it's the other chain that grabs this chain that balances this force. But there will be one point I cannot build up more because whatever I'm able to grab this chain is of a finite magnitude. So I reach a point that I cannot further build this, further stretch this chain. And that's the point of force imbalance. So it's discussed of course, in some great detail in the book, force imbalance. And upon reaching that force imbalance, this chain will no longer be able to further stretch because the other chain won't let it because it says, oh no, I cannot hold it anymore. At this point, they will mutually slide relative to each other. The further building up, elastic deformation is not possible. It starts to slide together, to slide together relative to each other. And we simply call that point disentanglement, for lack of a better word. What happens is this disentanglement, which is the same reason for wall slip. That wall slip, that red chain disengaged from the white chains, that's disentanglement. So this disentanglement will cause the structure to be much weaker at the place where disentanglement occurs. And there is a way to measure whether that disentanglement can, how much that disentanglement can mess up this homogeneous shear condition. In other words, you can imagine this is a true one, there's no structural failure. But if you imagine one monolayer start to disentangle, that layer will become weaker. That could produce an effect such that the deformation become noticeably like the orange line. That will give you a big correction. So your field will look like this now. And then shear bending will continue. But when this degree of entanglement is not sufficient, it turns out one layer of disentanglement produces no visible effect. What that means is, remember this is, it's not remember, let me emphasize, this is a horse race. Out of 10,000 layers, 100,000 layers, some disentanglement occurs first. If that disentanglement is not felt by the other chains in terms of how the other chain suffers the deformation, the other chain will also start to disentangle. At the end of the day, the disentanglement is uniformly taking place everywhere. In that limit, there will be no shear bending taking place, yet disentanglement still occurs, structural failure still occurs, overshoot still comes down, blah, blah, blah. So I hate to say that's a matter of luck, that indeed you need a sufficiently entangled polymer to demonstrate the effect that I indicated here, that you have seen so many times. Now let me come to the most difficult point here. All this to you sounds almost like now a piece of cake. The rubbery-like deformation ceases to occur because of disentanglement, because of reaching force imbalance. Therefore, I find myself less resistant as I shear more. So therefore, the force comes down, okay? I know we are in such a hurry. I apologize. We didn't get into any details. If you never heard about me saying stress, hear me one more time and last time. Stress just a way of capturing how much force is there. And since you may start with a sample where the shear device is this big, another guy may have a device that's only this big on the shear surface. How do you compare nodes? Well, his device is a factor of 4 smaller than my device. So his force, of course, will be a factor of 4 smaller. So you divide that force by the area, you get a quantity where your student A and student B can compare nodes. It's going to get the same thing. So that's why we call stress. It's a force per unit area. The area being the shear surface. Okay? All this is elementary. Now magic comes. So this is shear. You shear like this. The sample resists that shape change, and they find out that in the form of resistance is you find you have to have a certain amount of force acting on the surface, and which, of course, for a given condition is proportional to how big the surface is. So once you normalize the surface, you get this stress. It involves the load on a constant area. So speak about force is very convenient because the force is the same as stress, because the surface area is unchanging as I shear. Let me invite you to think about extension. You got a lovely piece like this initially, right? Even be a little fancy, you can see this three-dimensionally. And it has an area of A, 0 in the beginning. Now you're going to stretch. I know I'm running out of space. All I can tell you is when I stretch, I'm not going to draw this side because it's going to be longer. I eventually have a sample that's thinner, right? That's thinner now, right? In fact, no volume change. So if I have this little cross-section as A, then, of course, initial sample is L0. Then, of course, A0 times L0 is A times L. Now L is going over my board. Yeah? And you will trivially call this stretching ratio. Sure, who cares what you call? So that's what it is. So have you seen something dramatic here, different? Keeping in mind the loading surface is this two surfaces I'm grabbing on. What happened to it? Dimension. It's not constant. It's not constant, huh? It's not constant. It's not constant. I'm making a trivial point, so don't stare at me like that. I'm making a joke because this is the most amazing thing, because today, nearly all rheologists in the world has yet to appreciate of such a trivial point that you're staring at. So let me continue. Surely the area is not constant. And more than that, we know exactly how the area is changing because of this relationship. So by the way, we simplify it, we can just call this lambda. Okay. Keep in mind, all we're doing is trying to have a way to think about what the shape change does to your material in terms of when the shape change is fast, whether the material, how the material respond. Let me throw that to you. Does it also yield? Yield is the central concept in this whole 9 yard of nonlinear rheology, right? Which, by the way, is absolutely absent in the other 2019 book. Absent. Zero. In fact, there were some 40 words of yield used in that book. In all of the cases, it means to produce, yield, yield a result. So let me throw this to you, right? Which I already indicated. If shear undergoes yielding, no reason the same physics shouldn't apply. The extension should also, you should also encounter yield. Sample should also yield. Yield, remember, I repeat a few times, in our case, when you deform fast, yield is just a way of thinking about the structure being forced to fall apart in some manner. Homogeneous or not, localized or not. In the case of shear, I just patiently explained if you don't have a great deal of entanglement, it may just yield homogeneously. You don't see any feature of localization, so-called strand localization. In extension, well, what is the consequence of yield in extension? Assuming is such a bad word. It turns out you cannot, again, let's say it's the same physics, right? Yield because of force imbalance, disentanglement, and now you have millions of layers of now. Again, there would be a horse race, meaning some plane, or along some plane, a cross-section of plane, the yield, the disentanglement occurs first. That weakens, that part just draws more, and the rest doesn't, and it will just fall apart. So it will fall apart. And I was getting a little bit too fast, right? Impatient. This movie just shows exactly that. And you keep drawing, and the homogeneous drawing is impossible. It falls apart, actually. But I was not ready to give you the clue here. So what to do? I tell you what to do to confuse you. My job, I learned, I agree with it. Anytime you have confusion, it means the opportunity comes for you to learn. Meaning, if you're not confused, you will not have a chance to learn. Surely, I can write a stress like this. Force, that's required to draw, divided by the area at any moment. I don't know if the dot is there. At any moment, oh Lord, what is it? And go ahead and do it. T, or as lambda. So if you go ahead and do that, you'll find something like this. Or I don't like what I draw. it will basically do, I know why I'm not so smooth here. Basically, it will touching somewhere. It will do something like this. What you can tell? Well, for decades, people plot data like this. Well, when we were looking at this, we decided to look at differently. Motivated by the physics we already understand in shear. And we go back to what? We go back to rubber elasticity. So rubber elasticity basically is the idea that you can have I intentionally draw it not even because no network is perfectly even. But this is what they look like. Instead of cross-linking, we just have this uncrossability that I demonstrated. It's transient, but it allows you to form a network. I don't have time to draw all the dots there. And you're going to draw this now. It's three-dimensional, but I only have two dimensions to show you. You start to draw it. What you know from rubber elasticity is each of this chain will contribute certain force. So, for example, if as I draw, if I don't have any force imbalance or anything, as I draw, I still have 4 chains. Of course, this spacing now is more separated now. Then it starts to contract in the cross-section direction. Then as long as I look at this force, which is proportional simply to the total number of chains in that cross-section, and each of the chain contribute a force of F, little f. My force will just keep rising, right? In other words, this force is simply a product of how many of these chains are there. There are 4 of them. I wrote n of them because there are many more I didn't count. And each of the chain, as long as it's still part of the network, will have a monotonically growing force. Okay. So at least in one scenario, this total force will increase if each of the forces is increasing and if I still have this many chains. But the force imbalance and the disentanglement perhaps is exactly a case where this n will start to diminish, yeah? Some of the chain will start to disengage from the network. That's possible. And if it is doing that, then of course I can perceive that this will not monotonically grow and even come down as a result of n decreasing sufficiently, more so than f increasing. So it's all conceivable. Who knows? It's conceivable. So let's contrast. So we come to see, oh, same experiment, give me the data, I know how I represent it. I will represent it as F or as F, because for you to compare with another person who may be using a different, he may use a filament this thick, the other guy may use filament this thick. Of course, force will be different, but this quantity will be the same. The initial cross-sectional area. I don't know if you have followed the subtlety I have indicated here. This is not the same as what I advertised you here. Not the initial, but the instant cross-sectional area. This sometimes is called true stress, also called Cauchy stress, which is a famous mathematician of the past. This is known as engineering stress. Just definition. Don't bother. Just definition. It is directly speaks about the total force. Because this thing has nothing to do with where you stretch it to. It's the initial area. So how, okay, let me just give you this very disheartening experience. So when we first present this, or even if you present it today, you meet with trouble. You meet people who would tell you, oh, this is not a rheological variable, this engineering stress. I have no intention trying to confuse you, but this is, I'm trying to confuse you to drive home the point. There are people going to the extreme of accusing anyone using this as not using a rheological variable. I'm doing rheology. How can I be not using a rheological variable? What do you mean by that? Well, I know what they mean by that. According to the history, our dear polymer, as long as it's not cross-linked, is bound to be treated as a liquid. Don't tell me it's a solid, which I have been keep telling you it's a solid initially. It falls apart because it's a solid. It falls apart in shear bending in all these cases because it's solid-like. The structure is falling apart. Rheology, including polymer rheology, all can trace back their ancestors to Newton, to Navier-Stokes, to how we treat liquids, simple liquids. Since it's a liquid, you always need to update and report truth, as if this is the only truth. The moment, what the stress is. Well, it is this, of course. Let me give you a point that helps you a little more. If you go ahead and learn so-called numerical analysis, and people threw some equations for you and ask you to simulate, oh, when I stretch, how much stress is produced, you will go in some complicated geometry. It turns out you will solve that equation. Everywhere, you have to be careful using the so-called true stress, because that's where you can capture all the complicated geometries. So I understand you sometimes want to report true stress. But I'm just doing a damn simple stretching experiment. I'm not performing a fluid mechanical calculation. Moreover, no information lost, because this engineering stress is exactly related to the true stress by the factor of lambda. Why? Or you know why. I add A here, I divide A here. I add A here and divide A here. This is, of course, my true stress. This is nothing but 1 over lambda, according to this. Well, don't need to follow. This is just so trivial, it's not even funny to even mention it. So they are just related precisely this way. Okay? Look what happened. In this engineering stress measurement, or in representing your data of force in terms of this total force or engineering stress, you have the possibility of envisioning that your force or your engineering stress can reach a maximum because you start to lose entanglement. So you do it this way, as we did, or people just go bananas. And you know what happens? Oops. What happens is the very same data. Lord, this is what happened. I see. The very same data that give me this in engineering stress. Let me plot the very same data in true stress. Right? I just take that data, multiply that data every point by the lambda there is. You know what? As long as this drop is not as sharp as lambda, I know I draw it very poorly, there will be no peak indicated. In other words, this looks nearly featureless. I'm speaking about triviality. I mean, it's just complete triviality is what I'm saying. What happens physically, conceptually, is that as you stretch, even though you have yielding, you have start to lose force because of disentanglement, which means this F is dropping as I stretch more. But my cross-section is also shrinking. In fact, it can be in such a way my cross-section shrinks more than my force dropping. So when you look at this quantity, it never decreases. Get it? So just to be sure, this is the paper we published. And we show them there are certain features. We show them there are maximums, and we show them the maximum is followed by failure. And this could further be illustrated by saying that just like in shear, you could have before So this is all captured, summarized here, right? You could have, before this point, if you stop shearing and let go, it will come back. And after this point, when you let go, it will not return. And here's the two cases. Engineering stress during maximum, true stress is still monotonically increasing for the reason I have already indicated. The physics, the only way to capture the physics, was just a matter of choice. You always have 50% of being right. Is choose engineering stress, you will find a maximum, and that maximum, this is the raw data, the true data. And that maximum means if you are on this side and then stretch, you see, I can never demonstrate with this because I told you this internal length time is a fraction of a second. I can never stretch fast enough and control it while not breaking it. So by the time I let go, it doesn't come back anymore because it already through diffusion reached a different state. So it never could allow me to demonstrate this elastic yielding on this side. On this side, if you stretch and let go, it can never retract back to the original length. So is that not a proof? In other words, you can, this is the data, right? You can just go ahead and do such an experiment and appreciate this maximum by doing this two experiment. And you find out, indeed, that point seems to be a point of importance. So this is so much. This is how much, quote unquote, more complicated in extension, because unlike shear, where the load area is constant, this is a keep changing cross section, and you sort of have to recognize what captures the physics here. So lastly, I can. This remains highly confusing for my colleagues. Because I probably don't have more time to go into details. But basically, because of this forcing balance and disentanglement through a horse race in this extension where the elements are all in series, not in parallel, so any weakest link will lead to failure. You end up never able to stretch. This is where I'm not going to waste time here, and I will just use this mode to show you. So basically, there are different rate at which you stretch. In all cases, you fail to be able to draw your sample homogeneously until the flow state takes place. It always falls apart. In other words, undergo so-called strand localization. So this is one it does. This is at a higher rate. It may not be the same sample, so we're just trying to illustrate, forget about the speed of it, illustrate the different features that takes place. So this one, draw, and it involves a much larger region of inhomogeneity. And if you stretch even faster without cross-linking, however, you could even achieve this really remarkable situation. Okay, I'm stretching, and look at it. It breaks as if it was cross-linked, very, very sharply breaking. Okay? There was no cross-link. So the internal time of this, as I said, is a fraction of a second. I can never demonstrate this last one, region 4. I have to throw my arms away like a bullet to do that, which I cannot. So, but I do show you it breaks. Without even any hesitance, I tell you this breaking. Can you guys make a guess? This breaking I'm just demonstrating is which one? Not this one for sure, because the internal time scale is too short. I have to use a lightning speed to reach region 4. See, it's all about your external rate of shape change measured against the internal clock. This internal clock is just too short. So it's not region, we call region 4, this rupture. Can you speculate it's this one? Or it's this one? The short answer is this. This is a case the stretching rate is still relatively short compared to the internal clock. This is the case the stretching rate becomes a little higher compared to the internal clock. This is the case where the stretching rate is extremely high compared to the internal clock. So, in fact, this sample, because the internal clock is so short, anything I stretch will appear to be slow. Can you catch this concept? Because the T1 is compared with internal clock, right? Since the internal clock is very short, the T1 always appears to be rather large, which means my stretching is rather slow. I know you may have to make a few turns in your head to hear what I'm saying. So because this internal clock is so short, I can hardly ever stretch my sample fast enough relative to the internal clock. So I would venture to say it tends to be this one. In other words, no matter how I do it, I'm not stretching very fast. This three movie is in the direction of stretching slow, fast, faster. I mean the slow one. See, it breaks rather cleanly in some sense. And it turns out polydispersity also matters. The word you know, right? Polymers of different molecular in a given sample, there are different molecular weights in a sample, right? Depending on the nature we make the polymers, polyethylene certainly is rather polydispersed. Free radical polystyrene is certainly very polydispersed. Whereas this sample, in order to study the science of this, was made very monodispersed. In other words, molecular weight is rather narrow, chain lengths are relatively comparable, whereas this PDMS is highly polydispersed. And that polydispersity also affects this behavior somewhat. But that's a very detailed bit. So lastly, let me just show you a little bit of relevance to processing. So this is the processing. You're trying to rush it in a hurry, and this is the movie showing that. And the initial part is smooth because that initial part was pre-filled in the die and sit there and relaxed for a while. So the first part come out very smoothly. The new part that's coming out is through the rushing in of the polymer that comes out. Eventually, when you stop that, and this is actually there you see the smooth part and the rest of the part. Very ugly, very bad. So since we know what to do, we basically put a little camera at the corner of this entry and try to watch what happens as this sample is rushed into this little narrow channel near the end on the side. So you can see a wall slip-like behavior, all kinds of things. This one particularly shows, look at this discontinuity. It cut through leaving the rest of this alone. Look at this part, right? So this is a very severe form of disentanglement. and severely affecting the way the extrude comes out. So it's in that sense there is hope to finally help processing through the basic understanding of yielding, disentanglement, through forcing balance, and assess how strong the effect is even. So I think this is really all I wish to say. I can just stop this part.